And the first thing that'll happen, like it usually does, is it goes through initialization. And we'll see it go through that. There it goes. So it initializes display, buttons, the LEDs, the BME 680, the relays, and then it starts the hourly pricing monitor service, and it gives a start date time, just so I know when it started. And then we get a response back that it has attempted to start the monitor, and then now it calls back saying, hey, I've actually started the monitor. The next thing is the state machine gets initialized. The first thing that it does is it's forced into the idle state. So it transitions into the idle state out of startup. And the first thing that happens when it transitions into the idle state is that it must go into a delay. It must transition through a delay. And so you see a delay timer started. And all of the functionality inside the state machine is all governed through a threaded timer object. The whole thing may eventually be brought into a thread, but right now, because we're just moving between states and we have transitions between those states, the threaded timer works quite well because we're only ever really looking for an update every 1 to 2 minutes. And so it does, right now, it's polling and transitioning based on the polling. So for this purpose, because it's a relatively simple state machine, I think it's got 5 states and 11 transitions, maybe 10 or 11 transitions. So it's not a complicated state machine, but it's got enough to it that it's nice to have this partially threaded functionality, so that the intent is for it to be non-blocking. So it can go to a state, it's got to wait to transition, it goes in, it's sitting in that transition, and it waits until it actually fires off that timer that says it can move to the next state or checks its state. And so right now, there's one of the 2 timers has fired, and you can see it that it is checking state. And so an idling attempt has been attempted. It's been forced into that idling state, so it says I'm already in that state. And so the reason why this is happening is because this temperature and humidity is being evaluated every 2 minutes. And so that way it does a couple things. One, for right now, it eliminates the need for any sort of fancy filtering of temperature values. This thing kicks on, takes a temperature and humidity sample, turns back off again. It has filtering built into it already, so I'm just using the filtering that's built in to wait for a stable sample and then go back to sleep. And if you're sampling only every so often, instead of continuously sampling and then averaging, it's kind of a cheap way, but effective, to get averaging without really programming it, honestly. So after 4 minutes, the threaded timer will fire an event that will allow that timer to turn the delay flag back to false so that any cooling or heating function can start. And what this is really intended for, why it forces it to start with a delay, is primarily for the cooling system. And because this is going to automatically determine whether or not it needs to heat or cool in future versions, the state machine at its core is always going to assume when I power up, I'm delaying for 4 minutes. Because we're in cooling season, it's powering up and it's going to wait 4 minutes. Why does it do that? It is a feature that digital thermostats incorporate to protect the compressor on the outdoor unit, on your outdoor air conditioning unit. Why? Because after the air conditioner has run, the compressor and all of the high pressure side lines are at very high pressure. And if you shut off the system and then immediately try to turn it back on again, the compressor has to work really hard because there's so much pressure against it to start operating again. And so you might notice that if you ever short cycled your air conditioner, turned it off, turned it back on again with like an old analog turny thermostat, you might see all your lights dim a little bit more than usual, or you'll hear if you're close to the air conditioner, you might hear it make a sound that's quite nasty sounding. But so digital thermostats have a 4 or 5 minute delay to basically prevent that, to allow the pressure to bleed off. So you can see now the delay timer has ended. It's again trying to go back into its idle state, and it's saying I'm idle. So we haven't commanded it to do anything, So it's just going to keep going and checking to see, okay, I should go back into the idle state because there's nothing for me to do. You're already in the idle state, do nothing. So we're going to actually go through a quick example of starting the air conditioner. And so I'm going to go just turn the heat on, or sorry, turn the air conditioner on. And so I'm going to zoom down here. Okay, so we got it all in there. That way I can keep the little thing up there somewhere over here. So we got the lights, this, and this. So I'm going to go and set the air conditioner to turn it on. I actually have the jumper back in, so you will hear the relays come on, and it will start cooling. I guess I'll go really quickly through the user interface of this. The top is showing the current cost of the electricity, which is 0.9 cents per kilowatt hour. And that's averaged over a couple of samples in an intelligent way, which I'll go into in a separate video. And then below it is the inside temperature and humidity, pretty self-explanatory. Next to the inside label is this FCI. And what it means is it's degrees Fahrenheit comfort index. And it's a representation of the current temperature in this room or in the house based off of the temperature and the humidity. So it operates like a heat index, but it's been tweaked a bit to work inside. If I go in here and change the thermostat temperature, so I'm going to bring it down, and every time I hit that, the lights come on to indicate that I'm changing a set point. So I'm going to set it to 72.5 as the comfort. So it'll wait a few seconds and switch back, and then it will turn on the air conditioner because it's well below that FCI. And there's the cooling relay and the fan relay coming on. In the state machine, everything always comes on sequentially, never in parallel. So there's always an inserted delay between one relay coming on and the next relay coming on. That is to minimize the inrush current so that if we're running this off of battery, we're running it off of whatever we're running it off of, we minimize inrush current on anything that is being powered. The air conditioning has come on. Our set point, I can actually go look at the set point in another screen, which is the screen here, which kind of has all the nerdy stuff, which is the IAQ, the indoor air quality stuff, as well as the SPT, the set point temperature, which is 72.5. And so right now it's 73.22, and it's going to run to get down to that 72.5 plus or minus an offset. And that offset is a big next chunk of work. Right now it's a fixed constant. The next thing I'm working on is that offset becoming a parameter that can be modified. I'm actually going to do a separate video on describing that a little bit more and how thermostats work, and that'll be the video that follows this one. But basically this will run right now. Right now it's set to the default, which is 0.4. So right now we set it to 72.5, and so it will then come down to 72.1 degrees FCI, which is the comfort index, and shut off the air conditioner. To simulate that, I'm going to set this to just above that set point, which would be 73. Yeah, 73 should be just below it. And when that comes back, it should shut off, I think. Oh no, 73.1. So I might need to go up one more half degree. Actually, it has to go up a full degree because it's 0.4. So we're going to go up a full degree to 74. And then that'll be greater than our 0.4 delta or offset, and everything will shut off. When everything turns off, they just turn off at the same time. There's no need to actually do any sort of serial power off. Off it goes. So there it is, functioning. Everything is functioning. It's been running as our air conditioning thermostat for the air conditioning for about 2 weeks now. Haven't had a lot of necessity to run the air conditioning, but we've had a few opportunities to run it just to get the humidity out of the air, because over the last few weeks in the Midwest, Western Illinois, the humidity has been really, really high. In fact, I got a picture here of it up at about 71% inside the house. And that gets pretty nasty. So we closed the windows. I set this down to maybe a half degree just to get it to kick on. And the FCI, the calculated comfort index, is elevated because the higher the humidity, it adds to this actual effective temperature. The humidity may go from 71% down to 48% in the course of maybe 20 to 25 minutes, and then it turns off. And there's not really a need for the air conditioner to come back on again because it's pulled all the humidity out of the air, and it makes the place much more comfortable. If you would use a regular thermostat, it would have kept running and running and running until it got the temperature down to that point, and it would not have taken into account anything regarding the heat or comfort index. It's an interesting discovery. It's very much in its infancy, kind of playing around with the various ways to represent the comfort index, because what might be comfortable for one person may be uncomfortable for another. So this is just kind of a demonstration that it is possible to represent what we feel as temperature differently than just, oh, it's 73, that's hot, I want it to be 70. Because humans, our skin, our bodies, all of that, we don't feel temperature in that way. We might think we feel temperature in that way, but there's been study after study that has shown that that is just simply not the case. I kind of ignored what was going on in the console output. There's a lot of debug messages. They say info, but they're really going to be debug because they're not going to be printing for much longer. But you can see, I'll just point out that there's a cooling attempt started. Every time it goes through its 2-minute threaded timer, it checks to see, hey, do I need to keep cooling? And it checks and goes yes, because you haven't met the demand for cooling with that offset. So then it says, okay, I'm going to attempt to cool. Well, you've already started cooling, so you just stay back in that state. And then eventually it hits where the temperature starts to move down. Instead of, because when you turn the air conditioning on, sometimes you might get a slight increase in temperature. And so that's why you keep seeing it going, well, hey, I want to keep cooling, I want to keep cooling. And then eventually you hit a hysteresis band. You hit the band within the offset. So you have your upper limit and your lower limit. There they are, represented by my hands. And you're somewhere in the space in between there. And so you're in basically what I've called as a no action hysteresis band. And so that you just are sitting there going, okay, I have nothing to do, and I'm just waiting to hit that lower band or hit the upper band and attempt to start cooling again. So in this case, we came down a little bit in temperature, and we stayed there until I turned the temperature up to end the call for cooling, and then an idling temp was made. The delay timer was restarted because we finished cooling, and every 2 minutes it checks to see if it's in the idling state, and yes, it was, so it's saying I'm already in the idling state. So that's basically it from the console output. Anything else to note? I think that's it for an update. It's a lot. The next steps for this is to test it a little bit more, get this guy off the breadboard, even though seems to like sitting on it, and get it onto a break-off PCB and either mount it in here or just start working on the 3D printed enclosure and get everything together as one thing. If you have any questions or comments, leave them down below. If you like what you see on this channel, I would encourage you to subscribe, and I will see you in the next one.